Yes, students, let us discuss radius ratio rule for crystalline compounds. So, in crystalline compounds or ionic compounds, what will be there? One cation and anion. So, cation is smaller generally and anion is larger. But reverse also cases are there. Cation can be larger and anion can be smaller. We are discussing the examples. At that time, this concept will be the more clear. Now just pay attention towards this image. Sky blue colored large spheres are there. Means I am representing those as anions. Those are touching each other. Within those four, there is a gap. And in that gap, one ion can come. One ion can come. One ion can enter. Now in the first diagram, you are finding gap is more, ion is too small. So such status, such condition, such arrangement is not favorable. It is unstable arrangement. What does it mean? Relative to the size of the anions, cation is too small, or relative to cation, anions are too large. So this arrangement is not suitable for them. It is unstable situation. Now see the second figure in above image. There just a cation is touching the boundaries of the anion. So here somewhat it is sizable. Here stability is there, but case is limiting case. From here onwards, such a geometry, such a arrangement, such a structure may possible. Now focus on third diagram. Their size of the cation, that's a red ion, is increased further, causing separation between anions, and gap is completely already filled. So from second condition to this condition. Now in this third condition, space is there, gap is there between anions, so the repulsion will be less. But by the way, attraction between cation and anion will as was before. So this is somewhat stable situation. Now, question you may be with, up to where we can increase the size of the cation? Till the size of the anion we can increase that, so that radius ratio will equal to 1. Such cases are there in the metals where all are the same atoms. All the same atoms means sizes will be same. Then why not more than that? Because if you do that, then the reverse case will occur. Here we are focusing on gap between the ions, and that gap is filled by other ion. So suppose cation become larger than that of the anion, then the gaps between the cations will be filled by the anions. We have to choose that anion. Actually, it is not the case that cation only has to fill the gap. Anion also fill the gap between the cation. So we will understand it by various examples. Now again come to this figure A, or first figure. There, what is the conclusion? It is unstable situation. It means what? Number of anions which are surrounding are more. Decrease the number of anions. If we make it 3, chances are there that cation will be suitable. So number of ions surrounding the particular ion depends upon their sizes. Yes, sizes of both ions, cations and anions, and it is defined by one formula. It is defined by one term, and that term is radius ratio. Generally, considering cation as a smaller, we consider radius ratio as radius of cation to the radius of anion ratio, R plus upon R minus. Now question you may be with, why should we study this radius ratio? Wait. Now pay attention towards this representation. The figure which is represented at the top, it shows one cation is there at center and four large anions are surrounding that central cation. Actually only one cross section is represented here. In true sense, there is an anion which is above that cation. Means from our side, just imagine one anion. And sixth anion, which is from behind the paper or behind the screen. So actually that space which is occupied by cation is surrounded by six anions. So what is the name of that space? Octahedral space. And it is a limiting case for octahedral space where radius ratio should be, means ratio R plus upon R minus equal to 0.414. Suppose if this radius ratio increases, means size of the cation increases relative to the size of the anion. Then the ratio can increase as it reaches to 0.732, that octahedral structure can be retained. But if it becomes more than that, then what cation feels? I am larger. I can surround further more anions. As more anions will surround, more attraction will be there. More attraction, more stability will be there. So attempt of the cation will be to increase the coordination number. So in octahedral void when he was there, at the time coordination number was 6. So if that reduced ratio increases more than increases to value more than 0.732, its coordination number will become 8. So coordination number is increasing. Now see the other possibility. If we decrease the size of the cation, then the void remains unsuitable for that cation. That arrangement remains not fair for stability point of view. So see here. If the radius ratio is less than 0.414, then such octahedral arrangement will not be possible. Unstable structure will be there if octahedral void remains. So cation decides to get surrounded by means of lesser number of ions. Previously 6 were there, that will be converted to 4. Don't think that square planar 4. In tetrahedral void point of view, they will surround. And for that 4 anions, whatever the space tetrahedral void will be there, it is between 0.225 R to 0.414 R. Means if radius ratio if decreases up to 0.225, then coordination number also will decrease to 4. I repeat, to left side what is represented, if size of the cation increases, coordination number. What is coordination number? Number of other kinds of ion surrounding a particular ion will increase. And if you see the right side portion, if size of the cation decreases, coordination number will decrease. Right hand side, left hand side, coordination number increased from 6 to 8. From sodium chloride to cesium chloride, that's example. Right hand side, coordination number is decreased from sodium chloride to zinc sulfide. Cubic or spiral structure. You will understand it in more detail later on. Now this table is the summarized representation of radius ratio rule. What radius ratio rule says? If radius ratio is less than 0.155, then coordination number for that void will be 2, and a nature or type or site of that void will be linear. Second line, see, If radius ratio is between 0.155 to 0.225, coordination number will be 3. So 3 other kinds of ions can surround a particular ion, and nature of that void, site of that void will be triangular planar. Now see third line. If radius ratio is between 0.225 to 0.414, then coordination number will be 4. See, coordination number is increasing as size of cation increasing, and type of void will be tetrahedral. Now if coordination number is 6, increases to 6, then radius ratio will be 0.414 to 0.732. And if radius ratio is more than 0.732 to other limiting condition, that is 1, then coordination number will be 8. And what is the type of that void? Cubic void. And now these voids, cubic, octahedral and tetrahedral, those we have discussed. Now last portion is there for what the metals, where coordination number is 12. HCP kind of the packing may possible, or cubic closed packing may not possible if coordination number is 12 or radius ratio is 1. Now let us discuss this table or validate this table for their examples. Now let me take a type of void as a triangular planar. Example given is boron oxide B2O3. What is the size of boron plus 3, which is the cation present? Size is 27 picometer. And the size of oxide ion O minus 2 is 140 picometer. And if you take a ratio of the size of cation to the size of anion, means if you find radius ratio, you will get answer as 0.193. Yes, and that 0.193 comes in between 0.155 to 0.225. Therefore, coordination number will be 3. Around 1 boron plus 3 oxides ion will be there. The site name will be triangular planar. Now, let us discuss one of the example from next line. Let me consider zinc sulfide. There two ions are there, one Zn plus 2 and other S minus 2. The size of Zn plus 2 is 74 picometer and the size of sulfide ion is 190 picometer. So radius ratio 74 divided by 190, answer comes 0.389. Yes, and that 0.389 is between 0.225 to 0.414. So what should be the coordination number for that void site? Coordination number should be 4. So 4 different kinds of ions should surround one particular ion. It is a conclusion from radius ratio of zinc sulfide. Now let us come to the next line. Let me take example sodium chloride. Size of sodium is 95 picometer and that of chloride is 181 picometer. So what is radius ratio? 95 divided by 181. The answer is 0.525 and that 0.525 is between 0.4142 to 0.732. So what does it mean? Coordination number will further increase. Previously it was 4, now it will become 6 and the name of that void will be octahedral void. Now see the last example. Cesium chloride. The size of cesium ion Cs plus is 174. And chloride ion that we discussed, what was that size of chloride ion? 181 picometer. So take ratio, find radius ratio. So radius ratio for cesium chloride will be 0.961 and it is in between 0.732 to 1.000. It means the name of that void will be cubic void. So radius ratio rule gives us idea about which kind of void will be there, what will be the and how will be the occupancy of one particular kinds of ions. So in detail when we will discuss the structures, at that time this concept will be what clear. But it is sure radius ratio decides the size of the void, or more correctly type of the void, and accordingly in crystal structure arrangement varies. So students, from next part, let us discuss seven various types of cubic ionic crystals in detail one by one.